Now, you all know that I am also an astronomer. I have many hats. I'm an astrophysicist, I'm a physicist, I'm a solar physicist, I'm an astronomer, I'm a planetarium director. So, for this part of our study of circular motion and gravitation this week, we get to talk about space stuff right now. So, that makes me really excited. So, we're going to start by talking about gravitation by thinking about why doesn't the moon plummet toward the earth? Okay, the earth is exerting a gravitational force on the moon. The moon is exerting a gravitational force on the earth. Those gravitational forces are large because those bodies are so massive. So why don't the moon and the earth just smush into each other and collide? Well, the answer is because the moon is executing a circular motion around the Earth. This gravitational force between the Earth and the moon is equal to the centripetal force that the moon experiences as it's moving around the Earth. And so we've got the centripetal force of the moon's circular motion around the Earth equaling the gravitational force. And when we have those equal to each other, then you can create a stable orbit of a body around a stable orbit of a smaller body around a larger body. So you have to have the moon having some linear speed or angular speed around the Earth, and its centripetal force that it experiences has to equal the gravitational force between those two massive bodies in order for you to execute a stable orbit. That's what's happening throughout our solar system. So the gravitational force that I'm talking about is it's not the acceleration due to gravity, okay? It's a real force that exists between objects with mass. I am exerting a gravitational force on everything inside the room where I am right now. You're exerting a gravitational force on your computer. The Earth is exerting a gravitational force on you. The moon is too, all those things, okay? So gravity, or the gravitational force, obeys something that we call an inverse square law. The gravitational force is a universal force that affects all the objects in our universe. And Isaac Newton, who's the same Newton as our Newton's three laws, proposed that the force of gravity has the following properties. The force of gravity is inversely proportional to the square of the distance between the objects. Okay, so that means that if you double the distance between two objects, you reduce the gravitational force by them by a factor of 4. That's that inverse square. And then the force is directly proportional to the product of those two masses, the masses of the two objects in question. There could be many other objects, more than two in question, but the gravitational force is the product of the directly proportional to the product of those masses. So if you increase one mass, you increase the gravitational force overall. Also, gravitational forces are action-reaction pairs. For every action, there's an equal and opposite reaction. So that means that the gravitational force that mass 2 exerts on mass 1 is equal but in the opposite direction as the gravitational force that mass 1 exerts on mass 2. Okay, so in this situation, we would say, here's mass 1. We would call this force vector that's drawn in here the force that mass 2 exerts on mass 1, and that force is directed toward mass 2. The gravitational force is an attractive force. So because both of these forces are pointing toward each other, it wants to pull those objects together. And here, the way we're writing it is that the force that F sub 1 on 2 is the force that mass 1 exerts on 2. So this force that mass 1 exerts on mass 2 is going to be pointing off toward mass 1. And both of these forces are what we call an attractive force. That means it's going to want to pull those objects together. But you can keep those objects in stable orbits around each other by giving them circular motion. So here's the equation for gravitational force, or sometimes we call it Newton's universal law of gravitation. The magnitude that mass 1 exerts on mass 2 is the same as the magnitude that mass 2 exerts on mass 1, the magnitude of the forces. And that equals what we call big G, the gravitational constant, times the mass of object 1 times the mass of objects 2, divided by the distance between them squared. And that equation is also on your equation sheet. R is not necessarily a radius. It's really here, it's the distance between those objects. And this big G, this gravitational constant, it's a constant that exists throughout the universe, and it's 6.67 times 10 to the minus 11. Also on your equation sheet, the units are Newton meter squared over kilogram squared. So kind of a weird unit. And again, this is an inverse square law. You see that this quantity is proportional to 1 over the distance squared. That's inverse square. So that means that yes, doubling the distance between two masses causes the force between them to decrease by a factor of 4. Because if you've got 1 over r squared, if the distance is 2, you've got 1 over 2 squared. 2 squared is 4. So then that's the gravitational force becomes 1/4 of what it would be originally whenever you separate those two bodies by twice the distance. So again, in order for objects to be in orbit, a stable orbit around each other, Newton's second law tells us, well, we've got to have a force equaling a mass times acceleration. So that big F force is the gravitational force that those bodies are exerting on each other. And this mass times acceleration is the acceleration, the centripetal acceleration that smaller body is experiencing as it's orbiting around the more massive body. Okay, so then we have that our gravitational force, gravitational constant, mass of the first object times the mass of the second object divided by the distance between them squared must equal the mass times the centripetal acceleration. So that must equal mv squared over r, because we can write the centripetal acceleration as v squared over r. Here I have a diagram of, let's say, a planet orbiting the sun. So we've got the sun in the middle, big M, mass big M, and then our Earth is orbiting at some distance r, that's mass little m. And our Earth has a linear velocity vector here, tangent to the circular path. And we, the Earth, is experiencing a gravitational force. That gravitational force is the force that the sun is exerting on the Earth. So this gravitational force is the force that our big mass M is exerting on our little mass M. Okay, maybe we'll put a little sub E here to tell us that that little m is the mass of the Earth. Okay, so that gravitational force is pointing inward toward the center of the circle, is pointing toward the big mass, the mass of the sun. And Newton's second law tells us that the sum of all of our forces in the radial direction must equal the mass times the centripetal acceleration. So this little mass, that's the mass of the Earth, and then this is our centripetal acceleration, a sub c here. Now, the radial force that is being experienced is the gravitational force. And remember that the gravitational force is big G, would be the mass of the sun times the mass of the Earth, divided by the distance between us squared has to equal the mass of the Earth times the centripetal acceleration. Now, we can write this centripetal acceleration in a couple of different ways, but I'm going to write it as v squared over r here. Okay, so we see that the mass of the Earth cancels out on both sides. We could multiply, let's see, what do I want to do? We can multiply both sides by r, and then that cancels one of these r's down here on the bottom. So then we're left with the gravitational constant big G times the mass of the sun over r has to equal the linear velocity squared of us going around the sun. So square root that, v is equal to the square root of our gravitational constant times the mass of the sun divided by the radius of the circle, or the distance between the sun and us orbiting around it. So this is us deriving what is called the orbital speed of an object or a satellite around a more massive body. And so the orbital speed of the Earth around the sun is pretty close to the square root of the gravitational constant times the mass of the sun divided by the distance between us and the sun, okay? And you could translate this to any object that is executing a circular motion around a central, more massive body when we're thinking about orbits in terms of an astronomical sense. And now we're going to use all of that information in order to calculate the acceleration of gravity on the largest asteroid in the asteroid belt called Ceres, and also we call it a dwarf planet too. And this picture here is an illustration of what Ceres may look like.
Suppose you go to another planet or another celestial body. How would you be able to determine what the acceleration due to gravity is on that body? Well, you could drop an object on that planetary body's surface and see how long it takes that object to fall, and then you can use that with our kinematic motions for free fall in order to figure out what the acceleration due to gravity is on that planet or asteroid or moon, whatever it is. And we can also do it, figure out what the acceleration due to gravity is in a few other ways too, but this is what we're going to do for this problem. So we have an astronaut that is standing on the surface of Ceres. Ceres is an asteroid in the asteroid belt, but it is also classified as a dwarf planet. An astronaut finds itself on the surface of Ceres, and the astronaut drops a rock from a height of 10 meters, and it takes 8.06 seconds for that rock to hit the ground. And so our first question is, calculate the acceleration of gravity, or the acceleration due to gravity on Ceres. So G on Ceres is question mark. Okay. To solve this problem, we are going to use our motion for kinematics in one dimension for vertical motion. Because we're given a time to fall, we're given a height over which it falls. Okay, so we look back at our equation sheet. What do we have? We have an equation that says that y equals 1/2 acceleration in the y direction, t squared, plus velocity in the y direction, t, plus our initial y position. Okay, so using the same notation I've been using the whole time, here I'm going to set y is equal to 0, y naught is equal to 0 at the place where we drop the rock from. So that quantity here is 0. We're dropping it from rest. That initial quantity for the initial velocity is 0. I know my final y position. I know the time it takes to fall. I can solve this equation for y acceleration here, which is the acceleration due to gravity. On Earth, that's our 9.8 meters per second squared, but it's different for every planetary body, every celestial body. So we're going to solve this equation for the acceleration here. If I multiply both sides by 2, then I have 2y equals ayt squared. Okay? And then I can divide both sides by t squared. And when I divide both sides by t squared, I get that the acceleration in the y direction is equal to 2y over t squared. So that's going to equal 2 times my final y position is minus 10 meters over the time to fall, 8.06 seconds, and we're going to square that. So our acceleration due to gravity on the surface of Ceres is minus 0.308 meters per second squared. super small compared to what it is on Earth, the minus 9.8 meters per second squared. But so the acceleration due to gravity, this minus sign here tells us about the vector. It tells us that it's pointing downward towards the center of that planetary body. So the quantity g is just the magnitude of this acceleration. So the acceleration due to gravity on Ceres, if we're just thinking about what we call the surface gravity, which is the positive 9.8 meters per second squared on Earth, or the positive 0.308 meters per second squared on this planetary body Ceres. Okay, so that is a really, really small acceleration due to gravity, so that astronaut who's on the surface of Ceres better be really careful about making sure they don't bounce too much as they're walking, because it could be pretty easy for them to float off into space. So let's go on to part B. So part B of this problem asks us to find the mass of Ceres given its radius. Ceres has a radius of 510 kilometers. So 1 kilometer has 1,000 meters. So if I convert this into meters, we've got on 1 kilometer, there's 1,000 meters. So that is equal to 5.1 times 10 to the 5 meters. Okay. With that radius, we can find the mass of Ceres. So we're looking for its mass. Mass is equal to question mark. So we can say that the weight, this is the weight of our rock, which would be the mass times the gravity here, the surface gravity on Ceres, equals the gravitational force between the rock and Ceres. And so the gravitational force would be our gravitational constant times the mass of Ceres times the mass of our rock. Over here, this is also the mass of our rock, divided by the radius of Ceres, because we're going to now assume that the, divided by the radius of Ceres squared. We're going to now assume that that rock is sitting on the surface of Ceres. Okay, so this is the weight of that rock. Just like here on Earth, our weight is our mass times 9.8 meters per second squared. The weight of that rock on Ceres is going to be its mass times the acceleration due to gravity on Ceres. Okay, so that weight is equal to the gravitational force. It's the gravitational force that is giving that rock weight, and that's what this weight is here. So this gravitational force is responsible for this weight. Now if we look on both sides of this equation, we have the mass for the rock, which we can cancel out. So then we've got the gravitational surface gravity. Sometimes this is called the surface gravity. This gravitational acceleration is equal to our gravitational constant times the mass of Ceres divided by its radius squared. So if we just solve this for the mass of Ceres, we've got that the mass of Ceres is equal to the gravitational surface gravity of Ceres times its radius squared over the gravitational constant. So that's going to equal our 0.306 meters per second squared times the radius of Ceres, which we just found was 5.1 times 10 to the 5 meters squared. And we are dividing it by, oh, not 0.308 here for the acceleration. And we're dividing it by our gravitational constant, which is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. Okay, so I plug all that into my calculator, then I get that the mass of Ceres is 1.2 times 10 to the 21 kilograms. And so we can figure that out just based on the weight of that rock when it's on the surface of Ceres, and the fact that we already know what the radius of Ceres is. Well, what if we're asked to calculate the gravitational acceleration of Ceres at 50 kilometers above its surface. So this gravitational acceleration is going to decrease as you get further and further and further and further away from the center of Ceres. If we're 50 kilometers above the surface at 50 kilometers, that's where we're calculating the gravitational acceleration of Ceres now. So we worked ourselves over here in part B down to this equation where we said that the gravitational acceleration of Ceres on the surface is equal to the gravitational constant mass of Ceres over the radius squared. Okay, we can use that here. We can repurpose that same equation. It would be the same process. We would equate the weight of something at 50 kilometers above its surface to the gravitational force between Ceres and that thing at 50 kilometers above the surface. It would give us the same equation. So the gravitational acceleration of Ceres at 50 kilometers above the surface would still be our gravitational constant. So that's our 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared times our mass of Ceres, which we just calculated down here. I'm running out of room. Our mass of Ceres was 1.2 times 10 to the 21 kilograms. Okay, and then we divide both of those as they're multiplied together by, in this case, r is the distance between the center of Ceres and that thing that's 50 kilometers above Ceres' surface. So this distance here is going to be the radius of Ceres, 5.1 times 10 to the 5 meters, plus the 50 kilometers above Ceres' surface. Plus 50 and a kilometer is 1,000, so 50 times 1,000 meters. Okay? And we have to square all of that. And then whenever we plug that in, we've got our gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared over kilograms times 1.2 times 10 to the 21 kilograms, the mass of Ceres, divided by the distance between the thing at 50 kilometers above the surface and the center of Ceres. So we know the radius of Ceres right here, and we know we're 50 kilometers above the surface, so we have to add that. 50 times 1,000 will give us what 50 kilometers is in meters, okay? And so all of that stuff together squared in order to get the gravitational acceleration of Ceres at a distance of 50 kilometers above the surface. And when we do that, we find that this number is 0.255 meters per second squared. So at 50 kilometers above the surface, the gravitational acceleration is approximately 83% of what it is on surface. And I found that 83% number by taking the gravitational acceleration of Ceres at 50 kilometers, the 0.255 meters per second squared, dividing it by the gravitational acceleration of Ceres at the surface that we found over here in part A. And so at 50 kilometers, we're already at 83% of the surface gravity. So the surface gravity has decreased somewhat. For astronauts on the International Space Station, they are about 400 kilometers above the Earth's surface in the International Space Station. I had to look it up because I didn't have it on the top of my head. And at that height above the Earth's surface, the gravitational acceleration of Earth is only 90% of what it is here. Only 90%. So you lose 10% of the 9.8 meters per second squared whenever you go up to 400 kilometers above the Earth's surface where the space station is. Okay, so why do astronauts appear to float around inside the space station? Well, that's because the space station is in an orbit around the Earth. Okay, the space station is constantly in orbit around the Earth, is constantly falling around the Earth and always missing the surface. And the astronauts that are inside the space station are also falling around the Earth at the same rate. And so since they're both accelerating at the same rate around the Earth's surface, then they're going to experience some weightlessness because there's not a surface that they could stand on that would push back on them with a normal force that would give them anything like the normal force that we experience here on the surface of the Earth that gives us weight. So I know that when we were calculating the mass over here, we end up with units of kilograms because that's a unit of mass. But how did we get that unit of kilograms out of all this stuff that we were multiplying together? So that's something that we call unit analysis. And let me actually do that. I think it's important for us to think about that. So I'm going to erase some of this work right here so I can look at the unit analysis for this problem for part B that we went through. Okay, so we've got the acceleration, which is meters per second squared on top, and we're multiplying it by a distance which we square, so it'll be meters squared, and then we're dividing it by the units on our gravitational constant, which is a Newton meters squared over kilograms squared. So when you divide by a fraction, it's the same thing as multiplying by the reciprocal. Okay, so this is the same thing as meters cubed, because we've got meters times meters squared. So meters cubed over seconds squared times, we divide by the fraction, we multiply by the reciprocal, times kilograms squared over Newton meters squared. Okay, so let's see. We can meter squared here, and then we're left with just 1 meter on the top. So this is equal to meter over second squared times kilograms squared divided by a Newton is a kilogram meter over seconds squared. Okay, so now we have another dividing by a fraction, which is the same thing as multiplying by the reciprocal. So this is still equal to meters over second squared times kilograms squared times multiplying by the reciprocal here. We've got seconds squared over kilogram meter. Okay, so this, you could always say that this kilogram squared is over 1. So then we've got the seconds squared canceling with this second squared. We've got this meter canceling with this meter. And so now we've got a kilogram squared over a kilogram, and then that ends up just being units of kilograms, okay? So that's how you can do the unit analysis in order to figure out, or to prove to yourself that yes, it should be units of kilograms for our answer here whenever we were trying to calculate the mass of Ceres.